Greetings and welcome to 3dmotive.com. My name is Alan Thorne and I'll be your instructor on this comprehensive course introducing you to the Unity 5 game engine and its exciting feature set. In this module we'll explore lighting, textures and materials for real-time games. Using these features effectively will give you the ability to create believable and realistic looking worlds, the kind of worlds gamers will want to come back to time and again. We'll start here by exploring common light types, including point, directional, area and spotlights. Then we'll examine environment lighting, light mapping and pre-computed global illumination for achieving extra realism. We'll consider the differences between baked and real-time lighting, as well as its implications for in-game performance. In addition, we'll consider physically based rendering and what this means for you, and we'll see how to use the powerful and new Unity Standard shader. By the end of this part, you'll be familiar with a solid lighting workflow and its related theory for producing immersive results for your games quickly and effectively. So, let's get started. So in this section of the course we're going to be having a look at lighting in Unity, and I'm going to be showing you some of the things you can do to configure Unity for optimal lighting. The very first thing that I want to do before exploring the different light types is to show you how you can make a scene completely dark. That is, how we can remove all the lighting in the scene. Now, right now in front of me here I've got a completely new and empty scene. In fact, it's not quite empty. This is the scene that you will get if you move over here to the File menu and you choose File, New Scene, or press Ctrl-N on the keyboard. That will give you this completely new scene. But if we look in the hierarchy panel, you can see that the scene is not actually empty. We have here a main camera object that I've got selected here. You can see that over here. And we also have a directional light object, which is over here. Now I'm going to be going into the properties of the different light types later, but in short the directional light is good for simulating exterior light sources such as the sun and the moon. Now this light that is added automatically to the scene is connected to the world background, the skybox that you can see here. And we can create a day and night cycle just by rotating this directional light. So what this skybox does is it finds the brightest directional light in the scene. In this case it's just this directional light here because this is the only one that we have. And by rotating this directional light we can control a day and night cycle. So I'm going to press E on the keyboard to switch to the rotate tool, and as I rotate this light source you can see that it's changing from day and night. So I can rotate this to create a sunset, now a sunrise. Here we're at midday, I'm rotating around again, and then we're going to come around back to nighttime. So it's possible that we could script this light to rotate during the game to create a day and night cycle. But what happens if I want to make my game completely black? And I don't just want to switch it to nighttime like so, but I want to completely remove the light source from the scene, as well as the background data, creating a completely blank and empty scene in terms of lighting. Well, first of all, I could, for example, go Game Object, 3D Object and Cube, and we can see that indeed we do have lighting in the scene because, again, this cube is illuminated. Now, the first thing I might try to do to completely eradicate lighting from the scene is to select this directional light and press Delete on the keyboard to remove it. But when I do that, I do not completely subtract all the lighting from the scene because now we have a kind of a sunset scenario. And if I select this cube and I zoom in, you can see that this cube is still illuminated. If I switch over to the Game tab and get the view from the game camera, you can see that we can still see this cube. And that is because this environment, this skybox here, is providing some image-based lighting, some environment lighting. And in other words, this background is also acting as a light source. So I want to remove that information as well. Now to do that, I'm going to move up here to the window and choose Window and select Lighting to open up the Lighting tab. I'm going to drag and drop that here into the Object Inspector so that we can see the lighting information. And here on this section that says environment lighting, we have the controls for the environment lighting in this level. So what I want to do is to reduce the ambient intensity way down to 0. And under here where it says skybox, I'm going to set that here in the select material dialog. I'm going to select that and set it to none and then close that. And what we have now is a completely blank empty scene with no lighting at all. And we can confirm that because this cube now appears completely black. If I go to the game tab, we can see we've got a completely black cube. Notice the background isn't black, but that's simply an issue to do with the camera. I could select the camera and change its background here in the object inspector. Under the background property, I could change that from blue and change it to black, for example. And now we have a totally dark scene. I'm going to switch back to the scene tab. This effectively is the kind of scene we would have in previous versions of Unity where no lighting was added to the scene. So this is important for getting started with lighting, being able to create a completely dark scene that is devoid of any lighting, because in some environments, such as dark dungeons and caves, you may often want to begin with complete darkness and then just add to that by adding extra light sources. So that's how to create a completely dark scene. Let's move on and look at the different light types available in Unity. So now I want to consider the major light types in Unity, specifically the spotlight, point light, and the directional light. What I have here in front of me is a completely blank and prototype scene, basically. These are made using the prototyping primitives. So I simply created these by importing the prototyping package, by choosing Assets, Import Package, and Prototyping. And I've constructed this basic level here. All of the geometry is marked as static. If I select the root empty object that I've parented them to, and I select this, you can see that all the objects are marked as static, meaning that they will not move during the game. That can give us more realistic lighting. So what I'm going to do is I'm going to start by adding a spotlight to the scene. So to do that, I'm going to choose Game Object, Light, and then choose Spotlight. So this is one of the major light types in Unity, and it's pretty good for creating artificial ceiling lights, projector lights, and sometimes it can also be used to simulate natural lighting, such as sunlight or moonlight. So here I'm going to zoom in on the point light, and you can see that we've created this scene here, and the point light has been created by default below the level floor. Now the spotlight has two main properties. It has the light source itself and then a cone representing the direction and the range of influence of the light. So I'm just going to raise this up in the scene. I'm going to switch my coordinate space here from local to global. And I'm going to raise this object further up in the scene, like so. And just bring this over. Now right now the influence and strength of this light is so small, so trivial, that we really cannot see what kind of an impact this is having. So the first thing I'm going to do is I'm going to increase the range or the length of the spotlight. And I can do that by coming over here and changing the range value, or I can click and drag on the bottom point of the range and just pull that down. And when I do that, if I just zoom out a little bit and I pull that down, you can see the range of the spotlight increasing. So I'm going to increase it all the way down there maybe. I'm going to zoom in a bit further. And already you can see that this is already having a subtle effect. But I want to make the light a bit brighter. So I can do that by controlling the intensity slider here. So we have intensity, and I'm just going to raise this slider up here so that we can kind of see the effect this is having. I can also widen the cone here by changing the spot angle. So I can click and drag that slider, and you can see that this is increasing the size of the spotlight here. So I'm going to increase that slider. I'm just going to bring the spotlight up a bit here, and I'm going to rotate it as well. So I'm going to switch to the E key on the keyboard, and I can rotate the spotlight to begin to focus on something here. I'm going to focus on this. I'm going to switch my coordinate space from global to local rather, and then just pull that spotlight out, something like that. I'm going to increase the range maybe a bit more by clicking and dragging on the bottom portion there, like so. increase the intensity a bit more, and we get something like this. Now that's not looking too bad, but one thing I want to add to this light, and it's something that we can add to pretty much all of the lights, is I want to add a shadow. You can see that I have this cube here, and it's casting no shadow at all. If I select this cube, you can see we have a property here which is cast shadows, which is part of the mesh renderer component, and currently this is set to on. By default it's usually set to off. But I'm just going to make sure that on is activated. But notice that we still don't receive any shadows at all. So I'm going to select the spotlight once again, and I'm going to change here the shadow setting. Down here you will see in the object inspector, in the light component, that we have a property called shadow type. And right now this is set to no shadows. And we have the option to change this to hard shadows or soft shadows, where soft shadows usually gives us the best looking results. I'm going to select soft shadows here from the menu, and straight away you can see that now this cube has a shadow casting on the floor of the level, and if I rotate the light you can begin to see actually the effect that that is having here. Now notice I can rotate the cube, and you'll see that as I rotate the cube we have this shadow effect changing. So I'm just going to zoom in here, and if I look at the top of the cube, it may be difficult to see it in the viewport here, it may be difficult to see in the recording window, but there are lots of lines streaking across the top of this cube. It's artifacting that is caused by the shadowing effect here. Now I don't want that to appear on the top of my cube. I want to completely remove this distortion or artifacting. And to resolve this issue, you can select the spotlight here and change the bias setting. By increasing the bias setting, you begin to smooth out the artifacting in the shadowing here. So now I've gotten rid of that artifacting on the top of my cube, and it's looking much better. I think that the shadow the cube casts is a little too intense, and we can reduce that too by changing the strength setting here. So I can just reduce that slider down to something like 0.69, 0.71, and we're getting a much more realistic looking shadow here. So that's the basics of using the spotlight and its common properties, and these properties are pretty much common to the other light types, so I won't be revisiting shadowing again, but instead we're going to move on and have a look at the point light and the directional light. Now I want to consider the directional light and the point light in Unity. So the directional light is typically used for exterior bright light sources such as the sun or the moon, but it can also be used to simulate bounced lighting or indirect illumination, and we'll be revisiting that subject later in this course. So to create a directional light, I'm going to choose Game Object, Light, and then choose Directional Light. So I'm going to add a directional light to the scene. Now the important thing to bear in mind about the directional light, if I just change the local to the global world space here, so I can move the light around, is you'll notice that the position of the directional light is completely irrelevant to the illumination that is cast into the scene. It doesn't matter if the light's positioned here, it doesn't matter if the light's positioned over here. Position is completely irrelevant. What matters with the directional light is its orientation. It's supposed to represent a large light source infinitely far away, but what matters is the direction in which it is shining. So if I switch to the rotate tool and I begin to rotate the light, you can see that it's having an effect on the objects. They are changing their illumination based on the orientation of this light. So it's only the orientation that matters for this light here. So if I increase the intensity, and we've seen that slider before, I can increase the brightness of the light. So I'm just going to move this out of the way a little bit and just change the rotation, maybe something like that. We now have this directional light that is shining and casting illumination onto practically everything in the scene. I'm going to enable shadow casting for this light, and notice that straight away we only get one object casting shadows, and that is simply because when I select this cube, this is the only object with cast shadows enabled. I could select these other objects and again enable on for all of those objects, and suddenly we get shadows for these ones too. Let's enable shadows for these. And now we're getting shadows for all of the objects in the scene. And as I rotate the objects, for example, we can see as we move them around, suddenly the shadow moves with them. So that's the basics of how to use a directional light, and really it's useful mainly for sunlight. I'm just going to delete this light and completely remove it from the scene, and when I do that, again, everything goes back to black. Now let's consider the point light. Now it's time to consider the final major light type in Unity, and that is the point light. Now, the point light is perhaps the least expensive light, computationally speaking. For this reason, point lights are very commonly used in Unity scenes. So let's add a point light. I'm going to do that by choosing Game Object, Light, and then selecting Point Light. And point lights are especially useful for creating artificial lights, ceiling lights, wall lights, lamps, and pretty much any kind of artificial interior light that you can imagine, including candles. So I'm just going to zoom in on the light that we have created here, and you can see that it's pretty close to the ground. It's casting some illumination here. Now the way the point light works is it simply represents a light source centered on a point, and it casts light in all directions within the range of this sphere here. So this sphere represents the maximum range of the light, and beyond this, colors fall off to black. So right here we've got a range of 10, that's 10 meters. I'm just going to increase the range even further to something like this here. I'm going to increase the intensity of the light to maybe something like that. I'm going to raise up the light in the scene and just move it over here. And you can see the effect that this is having. Now to kind of get a tungsten light bulb effect, what I want to do is just change the color of the light just a little bit. So to do that, I'm going to move over here to the color swatch in the light component, click on this, and we get a color picker dialog, and we can pick the color of the light. So I'm going to switch to this yellowy kind of color to maybe something like that, and you can see here it's tinting that light already. So I'm just going to close this. And again, this light can also cast shadows. I can just move down here to the shadow type field and just select, for example, hard shadows, and straight away we're getting a shadow here. And as the light moves around, you can see that the shadows here are being cast on the objects. I'm going to add some more of these lights just by selecting this one, pressing Ctrl D to duplicate it, and then we're getting another light source. I'm going to select this one, press Ctrl D, and duplicate that over here, and straight away you can see that the effect this is having in the scene. And so you can see that really this is useful for a lot of interior scenes and can really create quite some powerful effects. So now we've looked at, in summary, the three major light types, and these are the directional light, the point light, and the spotlight. Now it's time to move on and consider color spaces. Now before proceeding any further with lighting, I want to consider an issue that is very important but is frequently misunderstood. And that is the issue of gamma correction and gamma space versus linear space in Unity. What I have open here in front of me is the asset store, and there is a free package available called the Shader Calibration Scene. So I recommend that you go ahead to the asset store and download that project and import it into your Unity project. It is provided by Unity Technologies and is available completely free of charge. This project contains a variety of sample materials that demonstrate physically based rendering in Unity 5, but it also is going to demonstrate the difference between linear space and gamma space, which are important for creating accurate lighting in your games. So I've already downloaded the project, so I'm going to exit the asset store here, and straight away here I've opened the shader calibration scene, which is called calibrationscene.unity. It will be imported into your project panel under the calibration scene here that you can find. So I'm just going to minimize the project panel down a little bit just to get some more real estate here. Now what I want to show here in the scene tab is the calibration scene that we have in front of us here. That consists basically of some planes and this kind of container in the center of the scene here. So I'm going to switch to the game tab, and Unity comes with two kinds of lighting models or color spaces, and these are known as linear space and gamma space. Now, to access the color spaces, you can choose File and then choose Build Settings. When you choose Build Settings, you get the Build Settings dialog appear, and down here you will have the Player Settings button. I'm going to select that and just move the Build Settings out of the way. In the Object Inspector, under the Other Settings tab, you will see for color space we have the choice of Gamma or Linear. Now, generally speaking, Gamma is the default, but if you want to work with physically based rendering, and we'll see what that is later, or if you want to produce lighting with the most physically accurate results, you should generally choose the Linear color space, and watch what happens to this scene in the viewport when I do that. So this is how it looks in Gamma space, and if I click Linear, we suddenly get a different appearance. Now, the difference in some ways is kind of subtle, but it is noticeable. If I go back to Gamma space, we get a slightly darker scene, and the shading is generally a little bit different. And if I go back to Linear space, we get this scene. So this is the difference between Linear and Gamma. Generally, Linear will produce more physically accurate results. But what I want to do is to jump over to a different viewport to explain some of the theory about what is going on, so you can make a more informed decision about whether you need to use Linear or Gamma for your project. So here I am in the Blender Node Editor. Now, you don't need to follow along with this. I'm just using this to give you a visual demonstration of the whole theory surrounding Linear versus Gamma space and why it is important for your Unity projects. In short, when an image or a texture file is saved on the computer, and on the left here we have this texture file, it is then finally at some point sent and displayed on the monitor, and we can see that here. Now, what happens when it's sent to the monitor is that because of various properties about the monitor, the image is always darkened. So I'm going to bring in this curve here. It's darkened by the same amount every time. And you can see that now the image has been darkened by this curve, the Gamma curve. This happens, there's nothing we can really do about this. It's simply that the image in the file gets darkened. So the way that we generally solve this problem is that whenever you save a texture file on your computer, a JPEG, a PNG file, or a Photoshop file, what happens is a brightening or a gamma correction curve is saved into the file. That is this curve. This is saved into the file so that the image is brightened, so that when it's sent to the monitor, it is darkened again, and it finally displays on the monitor at the correct brightness, because this brightening offsets this darkening. They negate one another and ultimately produce this linear curve or this linear space. So what happens when we use the gamma space in Unity is we get the texture files along with their gamma correction curve. So we get everything on this left-hand side of this line here. We get this file imported into Unity. And Unity will perform its calculations based on the image with this gamma correction curve applied. This means that Unity is actually working with an artificially brightened version of our textures, and this can produce inaccuracies in the shading calculations. When we set Unity to linear space, what happens is it takes the gamma corrected file and then it produces an additional curve, so this curve here. It produces this extra curve to darken the image and to put it back into linear space, like so. And then finally, when the textures are sent to the monitor, it applies an extra gamma correction curve so that the image finally displays at the correct brightness. So that ultimately is how it works. This is effectively what linear space does. It allows Unity to perform calculations, shading calculations, on the true appearance of the image and not the gamma corrected version. That is why when we use linear space, we produce more physically accurate results. But notice, physically accurate does not mean that it looks better. It just means more realistic. If you're making a game that isn't aiming for realism, you may not want to use linear space. But if you want to achieve photorealism, then generally going forwards, always choose linear space. For the rest of this course, I'm going to use linear space. So now I've opened up a Unity project called Global Illumination, and you can find this project in the course companion files. What I have open here in front of me is what is known as a Cornell box, or at least it's based on the Cornell box, and it's a great example for demonstrating indirect illumination or global illumination in Unity, and that is what I want to explore right now. Now, so far, based on the lights that we've seen so far, the point light, the directional light, and the spotlight, we've seen only examples of direct illumination. And indeed, in the scene that I have open here in front of me, I have some plane objects. I've simply created the plane primitives by choosing Game Object, 3D Object, and I've used a plane. I've also added a cube using the Cube option. So I've arranged these simple primitives around the level here, and I've marked them all as static to indicate that these objects will never move during gameplay. And I've also added a point light that you can see here at the center of the scene. Now I've docked the project panel just temporarily over to here, and you can see that I've also created some basic materials for each of these plane objects, so a blue material, green, red, and yellow. And I will explore materials later. But to create a material, you can simply right-click in the project panel, choose Create, and then Material. And once created, you can simply choose the color of the material over here using the albedo swatch. So I've created some basic materials and just assign them to the plane objects in the scene, creating this very basic setup. But there's some other things that I have done in this scene to demonstrate the difference between direct and indirect illumination. Firstly, I'm just going to go back over here to the hierarchy panel and select the point light. When I select the point light, you'll notice that the bounce intensity slider has been reduced to 0. Now, this is not the default setting when you create a point light. I've physically come in and just reduced this to 0. I have also accessed the lighting tab by choosing Window and selecting Lighting, and over here is the Lighting tab, and from this tab I have disabled pre-computed real-time GI. I have also disabled the baked GI checkbox, and I have also removed a tick from continuous baking. When continuous baking is activated, Unity will go ahead and calculate the indirect illumination automatically for you. But I have deliberately disabled these settings right now to demonstrate how they work. So in this scene here, you can see that we have only direct illumination. That means that only the objects that are directly exposed to the point light source here will be illuminated. The faces that are turned away from the light source, such as this one here on the cube and this one here, they appear completely black. Now that is unrealistic because in the real world, light bounces off of surfaces and bounces around. That means that the areas in these darker spaces should in fact appear darker than the surfaces exposed to the light source, but they should not appear completely black. They will just appear slightly darker. So what I want to do now is to activate all the options that we need to transform this scene from one using direct illumination to global illumination. To do that, I'm going to put a tick in the pre-computed real-time GI. I'm going to enable baked GI, and I'm also going to enable continuous baking, like so. And when I do that, Unity is getting ready to calculate the indirect illumination automatically, but still right now notice we don't have any indirect illumination. That is simply because when I select the point light and I move over here to the object inspector, the bounce intensity representing the strength of the bounce lighting from this light source, it is currently 0. But if I increase this slider, you will now see we have a scene that features indirect illumination. So now we are getting much greater levels of realism. In fact, if I zoom in, you will see that now the backs of this surface here are no longer black. They are still darker than this surface, and that is how we would expect them to be because they're not directly exposed to the light source, but still there is a certain amount of brightness to them. But notice also that we get color bleeding. That is, the redness from this red cube here is bleeding onto this yellow wall. You can see here in the shadow of this cube, we are getting a certain amount of redness where the indirect illumination is bouncing from this cube and hitting this wall and kind of transmitting its color onto that wall there. And we'll have the same thing going on the other side here, a certain amount of color bleeding, so that it produces a greater level of realism. So by simply ticking a few boxes, we have transformed this scene with direct illumination into one with indirect illumination, and it looks much better. In the next video, I want to go into more detail about this. Now, previously we saw the pre-computed real-time GI at work in Unity for producing indirect illumination in this level, and this is giving us color bleeding over here that we can see, and a general indirect illumination around the level where light is bouncing around the scene and is illuminating surfaces that are not directly exposed to the light. This makes the level look much more realistic, and this is a new feature of Unity 5. The great thing about this pre-computed real-time GI is simply the fact that you can move the light around the scene, for example, as I'm doing here, or you can increase or change the brightness of the light. So I'm just going to undo this and move the light maybe over here and just change the intensity of the light. And you can change all of these settings, and notice that Unity is able to still calculate where all the indirect illumination should be in this level. So you can move the light around, make changes, and still Unity gets the indirect illumination looking right, and that is pretty incredible. That works because ahead of time Unity calculates extra data called light propagation paths, and this stores information about how light bounces around in your scene. The one limitation to this is that it only works for objects that are marked as static. In other words, this cube, for example, has static marked, meaning that it does not move. And I will get back to the issue of what happens for moving objects a little bit later. So I'm just going to reduce the intensity of this point light again. Now, there is some other things that you can do. For example, if I switch back to the lighting tab, you will see that this pre-computed real-time GI is calculated automatically by Unity because I have this enabled and also the continuous baking checkbox enabled. If I didn't have that checkbox enabled, I would have to press the build button here manually. So this is a preference whether you want Unity to do it automatically or whether you want to initiate the calculation process manually. I'm going to leave this enabled. Now, if you have a scene in which your lights never move and never change, and the objects in your scene never move or change either, then what you can do is you can disable the pre-computed real-time GI and fall back onto the baked GI. Now, this gives you slightly better performance if you do this. So, for example, I can take the tick out of the pre-computed real-time GI. When I do that, Unity goes ahead down here and begins to calculate what are called light maps. That is, it saves the lighting data in the level to texture files. So I'm going to go ahead and let that bake. And when the bake process is completed, we get a slightly different look to our scene, but it still contains the indirect illumination that you can see here. I might have to tweak the brightness of the lights, but even so, you can see that we have the indirect illumination. And if I go over to the Light Map tab, let's just expand the Object Inspector here and select the Light Maps tab, you can see that Unity has calculated and saved out all of the lighting data into a set of texture files. But this method really does depend on the lights never moving or changing and the geometry never moving or changing either. For example, if I go back to the Scene tab here, beg your pardon, and I take a tick out of continuous baking, so Unity isn't automatically updating the lighting. If I select this cube and I move it out of the way, you will see that its shadow still remains entirely in place because its shadow is calculated into the level texture information. So I'm going to press Ctrl Z to undo that, and I'll re-enable continuous baking. I'm going to re-enable pre-computed real-time GI, like so. So in short, if the light never changes, the objects never move, you can rely on Baked GI to get some performance benefits. Otherwise, it's likely you'll be wanting to use Unity's new pre-computed real-time GI, and that's the option that I have reactivated there. But of course, there still is a limitation to the real-time GI, and that primarily is that it doesn't really work so well for objects that move around, such as the enemy character or the player character or other dynamic elements. For example, if I choose Game Object, 3D Object, and Cube, if I bring a cube into the scene here and I just use the scale tool to scale up that cube, I move it down to the floor here, just get that in line, bring that into the scene, you will see that this cube is illuminated very differently from this one. We have here direct illumination on this cube. We have the illumination here exposed to the light source, but these other faces are completely black because they're facing away from the light source. But notice if I go back to the inspector and I mark this cube as static, as the kind of thing that never moves, Unity, using the continuous baking, will go ahead and calculate that, and now we get indirect illumination on that cube. But this cube now, it can't really move around in the scene. So if I wanted this to be a player character or a dynamic element, I have to take the tick out of the static checkbox, but we don't get the benefits of the indirect illumination. Next, I want to look at how we can solve this problem. Now I want to demonstrate global illumination or indirect illumination for objects that move, specifically the player character in the case of this scene. This scene I have created here with just these geometry elements, and all of these have been marked as static. And I've added 3 lights, 3-point lights to the level, all of which have the range set as well as the intensity and the bounce intensity to provide for some global illumination here. In fact, I'm going to enable some shadows for these lights as well. So let's enable some shadows for this, and let's also enable shadows for this one too. So we have some shadows set for those lights. So I have this set up for the object. I just have to make sure that Cast Shadows is enabled for this object and also for this object. So what I want to do now is to add a player character to the scene and see how we can illuminate that character with indirect illumination. Now this scene has been assembled from a variety of packages that I have imported already. These packages are, if I go up to the Assets folder, Import Package, these include the Cameras package, the Characters package, and the Prototyping package. So I've already imported those. They can be found down here in the project panel in the Standard Assets folder. If I double click on that folder and I go into the Characters folder, you will see that we have a third-person character, and in the Prefabs folder we have a third-person controller. I'm going to drag and drop that object into the scene here. Press F on the keyboard to zoom in on that character, and we can see him here. You'll notice over here in the Object Inspector that this character is not tagged as the player character in the scene. I'm going to do that now by moving up here to the Tag option, clicking on this drop down and then choosing Player from the drop down box. So now this object is tagged as the player character. But the third person controller doesn't come with any kind of camera. If I switch over to the Game tab, you'll see that we see absolutely nothing because there is no camera in the scene. So I'm going to switch back to the Scene tab here, and I'm going to move back here to the Project panel, and in the Standard Assets folder and the Cameras folder, in the Prefabs folder, you'll see a variety of different pre-made cameras that we can use for our characters. I'm interested in the Multi-Purpose Camera Rig prefab, which is this one here. I'm going to drag and drop that into the scene, and I'm going to just position this camera rig by the feet of the character in the scene. So somewhere around about there, like that, will be good enough. I'm just going to drag and drop the Game tab to the side here so that I get a view of the Scene tab on the left and the Game tab on the right. Now I would like the camera to be slightly closer to the player character, so I'm going to expand the multipurpose camera ribbon, grab the pivot point of the camera and just move that down so that we're focused a bit better on this character here, maybe something like that. I'm going to rotate the camera just a little bit like that. And I think that should do that. I'm going to select the camera object here. And when I do that, you'll see in the object inspector that we have an auto cam script. I'm going to make sure that auto target player is enabled. This will focus on the object in the scene that is tagged as the player. And I'm also going to enable follow velocity so that we follow the player as he turns. And in fact, if I now maximize the game tab and press play on the toolbar, I can use the W, A, S and D keys on the keyboard, and this now has completely configured a third-person character controller, and we can follow that character as he moves around the scene. Now we can see that this character is being illuminated, but he is being completely illuminated by dynamic illumination, by dynamic lighting. That is, Unity is calculating the lighting for this character in real time. We are not receiving any kind of global illumination on the character, and we can prove that by selecting the character object. And if we move him to the edges or the limits of the scene and zoom in on him, we can see that this side that is turned away from the light is completely black. So this character receives no global illumination at all, and that is what I want to address now. So to add indirect illumination to our real-time models, that is the dynamic models that move around in the game, we can use a feature called light probes, and these sample the light at various points within the level and then use that to blend the data or the lighting across the model. In short, light probes will allow us to simulate the appearance of indirect illumination on moving characters. They are not as realistic as the pre-computed real-time GI, but they usually provide a good enough approximation. So to get started, what I'm going to do is I'm going to create a completely new and empty game object by choosing Game Object Create Empty, or I could press Ctrl-Shift-N on the keyboard. I'm going to select that here, and I'm actually going to just, center that at the origin here. And I'm going to name this object Light Probes. That is not essential, but that's merely for my reference and readability for the objects here in the hierarchy panel. So to create light probes, I'm going to select the empty object that I created, and I'm going to choose Component, Rendering, and then choose Light Probe Group. So I'm going to select that option. This will then add a light probe component to the object here. And you can see here at the center of the scene, we have a variety of these circular objects, and these are the light probes themselves. So what I can do is select one of these objects and then just move it over here. Now by doing that, I'm moving a light probe to this point in the level, and it's recording the light at this position. Let me just press Shift Spacebar to maximize the viewport here. So this light probe is now recording the level of the light at this point in the scene. So I'm going to put it maybe about here. I'm going to select another one of these probes. Let's say this one. Let's focus in on that. I'm going to move this to this point over here. Maybe raise this up a little bit like so. I'm going to select this probe over here and move it over to this position in the level. So we're getting maybe some darkness at this point. Again, it's recording the light information at this stage here. I'm going to grab this probe and I'm going to bring it over here. And the idea is to try to move these probes in key areas in the level where the light changes. Actually, I'm going to raise this up to around about this point in the level. So I'm going to select this probe and raise that up into the level over here, maybe somewhere around here. And then I'm going to come in and begin to select these other probes that are all the way down here. So let's select this probe. I'm going to move this up to the floor level. Let's pick this probe. I'm going to raise this up a little bit. Let's just move all of these probes up in the level. Zoom out and move this probe over here. Let's bring that down to record the light in the level at this point. You'll notice that as I move these probes around, that the light in the level begins to flicker a little bit. And that is simply because I have continuous baking activated. Unity is continually trying to rebake and recalculate how the level would appear. So notice right now that we're suddenly getting illumination on this side of the character model. I think that maybe it's a bit too bright. And if I select this lamp, if I just come out of the main maximize viewport here and select this light, you'll notice that as I select it and I reduce the bounce intensity for the light, that actually this model begins to darken up so that we can see that this character model is indeed being affected by the global illumination in the level. So now when I press play on the toolbar and I start to walk the character around the level, finally we're getting illumination that is being received from the light probes. And right now it's a little bit bright, so what I would probably do would be come back in and start to reduce the bounce intensity of some of these lights in the level. But apart from that, we can see that this character is now being illuminated by the light probes that are strategically positioned at various key points in the level. I may come back in and start to tweak the positions of some of these light probes a bit further to sample in slightly better places. For example, we've got a big gap between this probe and this probe, so I might in fact select this probe, let's say, and start to bring that over here. If I wanted to add more probes, I can do that too, by coming over here and clicking the button that says Add Probe, and that will generate a completely new probe in the scene here. So I'm just going to reduce that down, and we're starting to get a more realistic approximation for the lighting for this character. If you have a character that appears to be unaffected entirely by light probes, then make sure that you select your character mesh in the level here. So right here we've got the third person controller. I'm going to expand that and select the body mesh for this character. And notice in the skinned mesh renderer component, there is a checkbox for use light probes. You'll want to make sure that that is enabled for all the dynamic meshes that you want to be affected by light probes. So we've seen here a very quick way in which we can get our real-time models affected by the lights in the scene, and that's looking good. Now I want to consider the issue of physically based rendering in Unity, or physically based shading. Both mean the same thing. So far in this course, we've seen a method for creating lighting, both direct and indirect illumination, and we've also seen gamma and linear space workflows. But all of that really is just one half of the story to creating good-looking scenes. The other half is about building realistic materials, and Unity provides us with a new kind of material type called the standard shader, and this is part of the physically based shading system. In short, physically based shading doesn't refer to a specific thing or even to a specific process. Rather, it refers to a collection of processes, and these processes together try to place certain limitations upon you so that you can more easily create realistic materials. What I have in front of me here is the shader calibration scene that we've seen before, and you can download this for free from the Unity Asset Store by searching for the calibration scene, the shader calibration scene. And when you import that scene into your project, you'll get a range of different folders here. Of particular importance are the PBS metallic and the PBS specular folders. The PBS stands for physically based shading. And in Unity you have two different approaches for creating physically based materials, and these are the metallic workflow and the specular workflow. There's no right or wrong way. You can use either. Right now I'm going to have a look inside the PBS specular folder, so I'm going to double click on that. And inside you'll find a whole different range of pre-made material types. So for example, here we have mud. If I select the mud material, you'll see that we have the standard shader applied. Over here we have the shader type, and that allows us to create different types of materials. If I click on that drop down, you'll see we have standard and standard specular. These two material types are newly added in Unity 5, and both of them refer to the standard shader. The standard shader is the metallic workflow, and the standard specular is the alternative approach, but both can produce physically based materials. So this material, the mud material, is using the specular workflow, and we have an albedo map, a specular map, normal map, and a height map, and it's configured so that it will look realistic. For example, if I drag and drop the mud material onto this container, you can see that now it looks like mud, and this will look good under a range of different lighting conditions, so that we could completely change the lighting in the scene, and this still will look like mud. I could, for example, change this to maybe a kind of silk look here. I can drag and drop the silver to make it look like silver. Again, I can drag and drop a kind of fabric look onto this to make it look like a fabric. Again, I can do the same with the brass material. So we have a range of different materials that are all pre-configured for us, and we can use these as a kind of reference to build our own materials. So that's a basic introduction to physically based shading. I'm going to be having a look at this further next. Now I want to move further to examine physically based shading in Unity by creating some physically based materials from scratch. Now I've got a scene here with just some objects in here. All of them are marked as static, and it's just a basic new scene. So we have a cube, a capsule, a sphere, and plane primitives. And you can find this scene in the course companion files in the folder PBS materials. So we have this scene here, and I want to start out by creating a metal gold material. Now when we use the shader calibration scene, that scene comes with a PDF file that is inside the project panel that you can open up to find out how you should configure your different materials. So for example, I want to make a gold material, and I can bring that PDF into view. This is the Unity specular chart.pdf, and again this is part of the shader calibration scene, and it divides our materials into several steps. So we have the albedo RGB, we have the specular RGB, and we have this smoothness value. So I'm just going to set this to one side. I'm going to be coming back to this in just a moment, but I just want to make you aware that I'm going to be using this chart to build a physically based gold material. So I'm just going to move this out of the view here. To create a completely new material, I'm going to right click inside the project panel, choose create, and then choose material like so. I'm going to call this mapped gold. Actually, I pressed enter by mistake there. Let me just rename that, mapped gold, like so. And over here in the object inspector, you can see that by default, this matte gold material is set up to use the standard metallic workflow, but I'm going to use the specular workflow. So I'm going to switch this from standard to standard specular. And here we have several properties for our gold material. Now I'm going to bring in back that chart that we saw before. Now for metals, you will notice that the albedo, the RGB values for the albedo map or the albedo texture should in fact be black. So generally black for pretty much all kind of metals, gold, brass, copper, iron, platinum, aluminium or silver, all of those are completely black. So I'm just going to move the chart out of the way and go over here to my albedo slot and click in that color swatch, and I'm going to choose the color black, like so. And you can see the effect that this is having in the preview window right now. Notice we still have some details on here, and this is controlled by the specular setting and the smoothness value. The specular color controls how shiny or reflective the object should be, and the smoothness controls how the reflection is dispersed. So for example, we could have a mirror-like surface by setting the specular color to white and setting the smoothness very high, so we have practically a mirror effect. But we could keep the surface just as reflective and yet turn down the smoothness, and now we have a much more blurry and reflective surface, and here in the center we have a partial blurriness. So you can see the effect that that smoothness slider is having there. So I'm going to bring back the shader calibration chart here and scroll down to the specular setting. And in the specular setting, we can see we have some example values as to what the specular should be. So for gold, it should be this color. So what I'm going to do is just move this out of the way. For the specular slot, I'm going to click on the eyedropper tool, and I'm going to move over to my PDF file and just eyedrop and click on that gold material. So now that color for the specular has been set. And finally, to determine what the smoothness value should be, again I'll bring back the calibration chart and scroll down here to the smoothness setting, and notice that generally the metals pretty much should be set to 1 or something quite smooth for a metal. So I'm going to set this the smoothness to the gold material here to something quite high, maybe not quite exactly 1, but maybe something kind of like this. And then I will drag and drop that onto the sphere, and notice now we have a physically based gold material on this sphere. So that's looking pretty good, and that's the basic workflow on how to create a physically based material. You can use the shader calibration chart to guide you on how you should configure the maps, the colors, and the smoothness setting for the material. In the previous movie, we saw how we could create a physically based material to create a gold effect, which was applied to the sphere that you can see in the scene here. Now I want to move forwards and slightly refine the look of this material. If I just click on the sphere and press F on the keyboard to frame that, I'm going to maximize the scene tab here, and we take a closer look at this object. We can see, as any gold material should look, is that it is reflective. Inside this object here, I can see the environment reflected. We have the light source, the sky, and the ground area, but there's something that we don't have. We don't have this ground plane mesh here, neither the cube or this capsule mesh here. None of these feature in the reflection of this sphere, and I want to correct that now. We can do this by using reflection probes, which work a little bit like light probes, except rather than sampling the light levels, they sample what the reflection would be. So I'm going to come out of the scene tab here, and to add a reflection probe, I'm going to choose Game Object and then create empty, or I can press Ctrl-Shift-N on the keyboard. I'm going to rename this object Reflection, and I'm going to center it at the world origin, like so. So now we can see the object is centered at the world origin. Now I'm going to select the reflection object, and to add a reflection probe, I'm going to choose Component Rendering and then choose Reflection Probe from the menu. When I do that, you can see that this object here, this sphere, this invisible sphere, is added to the level. And what it does is, from this point, it samples how the scene would be reflected. You will notice that the reflection it generates is in fact updated here in this sphere. Straight away we now get reflections of the objects inside this sphere, so we can kind of see the reflection that's going on here. Notice if I zoom out and I have the reflection probe selected, it shows me this cube-like boundary, which means that any reflective objects within that boundary will use the reflection that is sampled from this probe. This means that if I select this sphere object, this one here, and I move it outside of the probe, notice that the reflection then goes back to what it was previously, because it's outside the range of the reflection probe. I'm going to press Ctrl-Z to just undo that and put the sphere back to where it was. Notice also if I select the reflection probe and I begin to move that around in the scene, that this changes the reflection that we get in this sphere. And actually now we can see that when I rotate from this angle, we can see based on where the cube is and the capsule is here, we're not getting a truly accurate reflection for this sphere. So if I wanted to get that, what I would have to do would effectively be to move this sphere where the sphere is here. So I'd have to overlap the reflection probe with the sphere and raise this up in the scene. And now what we're getting is a much more accurate and realistic reflection. Actually, the gizmo for this reflection probe is kind of getting in my way. I can control that by moving over here to the gizmos option, and I can kind of just reduce the size of the 3D gizmos here. So here you can see inside this sphere now, based on the reflection probe, we're getting a much more accurate reflection that does counter the two objects here. And in fact, if I were to select the cube and just move that off to the side, Unity would recalculate all the reflections, and we would see here that the cube has now moved in the reflection for this object. So that's basically how you can deal with reflection probes to produce very realistic looking reflections for your materials. So in this final stretch of the course, I want to consider the issue of emissive lighting in Unity 5. This is a new feature that is part of the standard shader, and what it allows us to do effectively is to use our materials as a light source so that we can encode the material in a particular way, allowing our objects to cast light. This means that we can create light of all kinds of unusual shapes, and it's particularly useful for neon signs or for wall lights, for example. So what I have in front of me is a completely blank scene, or rather it's a scene with 3 cubes and a plane, and I can turn off lighting to see these. But I have removed all lighting from the scene. I have deleted the directional light, and I've moved over to the lighting tab and have removed all the environment lighting information. We saw how to do that in an earlier part of this course. So I have a scene with all lighting removed, and all of the objects that we do have, these 3 cubes and the plane, they have all been selected and marked as static so that they can receive the pre-computed GI information as well as receive lighting from our physically based materials. So what I have to do to get started at using emissive lighting is I have to create a texture map that is going to define our light source. So I'm going to jump over to Adobe Photoshop, and when I do that I'm going to bring up this texture here that you can see. Now this is a pretty basic black and white texture that I've created very quickly in Photoshop. I simply produced a circle here and then I cut it in half by using the Marquee Select tool. So we have white areas and black areas. Black areas represent areas that are not going to cast or emit any light, and the white areas represent areas that will cast light or will glow. So I'm just going to exit Photoshop and go back to Unity, and I'm going to drag and drop our texture here into the project panel and release my mouse, and this imports the texture here. This is a 512 by 512 texture. That's absolutely fine. All of these settings for the texture I'm going to leave at their defaults. So to create emissive lighting, I need to produce a new material. We already have our gold material that we created earlier, and now I want to create a new material. So I'm going to right click in the project panel, choose create, and then select material. I'm going to call this matte and light, like so. I'm going to select that material. Now, because this material is going to act completely as a light source, I'm going to switch this from the standard shader to the standard specular setup. But I want the specular, the shininess, to be completely black. I'm not interested in the shininess of the material. And again, for the albedo, I'm not really interested in that either. So I'm going to completely hide that as well. And for the smoothness, again, I'm going to reduce that to its lowest 2. So completely black. But what I am interested in here is further down is the setting that says emission. I'm going to drag and drop our texture into the emission slot. And if I ever want to see what that texture looks like as a quick preview, you can hold down the Control key on your keyboard and click to receive a quick preview of the image there. But in any case, I'm just going to select that material, and in the emission slot we have the material that I've plugged in here. And I can increase the strength of the lighting if I want. I'm going to come back to that setting. But what I'm going to do now is drag and drop this material onto, for example, this cube. I'm going to drag it onto this one as well, and finally onto this one. And notice straight away that although I've dragged the material onto these cubes, notice the effect that this has had on the floor of the level. See how the floor of the level has received the illumination cast from the surface via this emissive map. If I wanted to increase the brightness of the light sources, I can simply move over here to the emissions panel, and in this setting here where it says 1, I can increase the strength and the intensity of these light sources. And again, we have a color swatch here which allows me to multiply blend a color on top of the light source. So for example, I could pick the color blue and then just change the tint or the color of the light source so that now this is emitting a kind of bluey purpley light. I'm going to increase the intensity just a little bit more, like so. And that's looking pretty good. You can see the effect that now is having on this light source. Notice, however, that although I changed the color of the light source from this swatch here, it does not update the color in the texture file. That remains the same. So you may want to align the color in the image with the color that you use in the swatch here. So we have our basic light source set up, and this looks quite nicely, but notice that all of these objects that I have in the scene are marked as static. If I choose Game Object, 3D Object, and I put in a cube in the scene, and I just scale this up a little bit, you'll notice that this cube, being a dynamic object because it's not marked as static, does not pick up any of the lighting information from these light sources, from these materials. But we've seen already how we can easily fix that. You may remember that we covered the issue of light probes and how that can help dynamic objects, and we can apply that same principle here. So I'm going to choose Game Object, Create Empty. I'm going to center that at the world origin, and then choose Component Rendering, and I'm going to add a light probe group. And when I do that, we then get all the light probes added to the scene. You can see those light probes added here. I'm just going to select one of the probes here in the scene. Let's just click on, for example, this one. And I'm just going to move that to a completely different place in the scene. And the idea is that you will space out all your probes as necessary, but notice straight away that this dynamic object, the cube that we have added to the scene, that is now being blended between the probes in the scene. And actually, as I select that object, we also get a visual indicator in here drawn between the probes that are being used for the blending process. So now this cube, although it's a dynamic object, is still being affected by the emissive lighting from the materials. So that allows us to achieve some pretty impressive results. So this concludes the lighting portion of this course. I hope you found it helpful. My name is Alan Thorne. You've been watching 3dmotive.com. Until next time,